Better?
Oh, yeah, can you hear me okay?
Yep.
Perfect.
Yes, I logged in and got the audio set up at exactly the moment that you coughed loudly.
Yeah. Great. So let's get started. Hello, good morning, everyone. Again, thank you for braving the cold, and welcome to those of you who are live streaming. So just a couple quick announcements before we get started. So if you were not able to attend the algebra review, but you would like to watch the video, I've linked that in Moodle under the Getting Started tab. So that video is posted, just going through those algebra problems that I'd asked you to look over. So this week, The review on Thursday, and then next Monday will be on graphing. We'll talk a little bit more about that on Thursday. But if it's been a while and you don't remember graphing properties, this would be a good review to attend. So today we're going to cover just sort of a hodgepodge of different things that we have to review just to remember for our work in calculus. So we'll sort of be bouncing around there. As I mentioned in my email, if you are not familiar with supply and demand, you're going to want to watch the supply and demand asynchronous video. It's pretty short, so just making sure you understand sort of the general concept so that we can apply some of the stuff we're learning today to that as well. So today we're going to be doing some definitions, some practice problems. We're going to go a little bit fast today just because we do have to cover sort of 3 different topics to go through. But hopefully it's mostly things that you've either heard before or things that make sense as we go. Obviously, if there's any confusion or things you need clarification on, you can come by drop-in help in office hours anytime. We're happy to look at that with you. Also, at the end of class, if you have a question, you can ask a TA, you can come up to the computer and ask me. That's totally fine. So we're going to get started. So I'm just going to switch over to the dot cam. All right. So the first stuff we're going to talk about are applications of functions to economics. So in this course, we try to do a lot of applications because it's applied calculus. And there's sort of 2 big sets of applications we do. We do applications to the life and social sciences, so biology and chemistry. And then we also do applications to business through the lens of economics. So if you are in business or econ, you'll see this stuff in the work that you're doing. And then we'll notice when we get to the life science type things. So in this course, we don't assume that you have taken any economics or anything like that, which is why we're going to go through some of the terminology so that we all are on the same page when we talk about these types of things. So the first thing we're going to talk about is what's called cost. So whenever we're talking about business, we are always talking about it from a manufacturing standpoint. So what does that mean? That means we are assuming that we are the person who is making and selling some sort of product, okay? And so when we talk about cost, we're talking about how much it costs us to make a product, okay? So let's say that you are going to make, trying to think of something, you're going to make pianos. I don't know, maybe you're in the piano business, right? When we talk about cost, we're saying how much does it cost me to make and manufacture one piano, right? So that's what we're talking about when we talk about cost. And for now, we are assuming that everything is linear, okay? And the reason we're doing that is because we only know how to do analysis with linear functions right now. We talked about this a little bit last time. We're building everything from linear functions. We will work through this with linear models in chapter 1. And then in chapter 2, we'll say, well, what if it's not linear, right? What do we do? So we will get to that. So for now, we're going to think about this as a linear function. So cost, you're going to see as C of Q. Q is quantity, so the quantity that you are making. So if you make 1 piano, it costs this much money. If you make 2 pianos, it costs this much money, so on and so forth. So there's 2 parts to cost. There's what's called the fixed cost, and then there's the variable cost, okay? So the fixed cost is going to be your cost even if you have not made anything, right? So this might be like buying a warehouse, right? You only buy it once. It might be some sort of fancy machine that's used to put all the strings in. You buy that one time, right? So fixed cost is anything you pay sort of upfront before you make anything. Variable cost is going to be the cost that depends on how many are made. So wood and, piano keys, right? That's all variable cost because it depends on how many pianos you make. So these 2 pieces together are going to be what help us form our cost equation. So the variable cost, right, is the slope of the line. So for every additional piano you make, your cost increases by that variable cost. Your fixed cost is your plus B. It's the amount that you would spend when quantity is 0, okay? So when we talk about the variable cost, we will also refer to this as marginal cost okay? Because what marginal cost is the additional cost to produce one more. And since we're talking about linear functions, that's just the slope of the cost function, okay? So we'll talk about marginal costs in different ways, but for linear functions, it's just that slope, okay, that variable cost. So let's consider the two following scenarios. So we'll just look at the first one first. And we want to draw a graph of a linear cost function that satisfies the given conditions. So I want you to quickly sketch in your notebook or wherever you're taking notes, a cost equation. So it's a line because we're dealing in linear, where the fixed costs are small, but the marginal or variable cost is high. Okay, so think about what that means. Fixed costs are small. Which part of the linear equation is fixed cost? Marginal cost is high. Which part is the marginal or variable cost? And then just draw a line that would satisfy those two conditions. So quickly sketch something up. I'm going to give you about 30 seconds to try to guess what this is going to look like. Okay. So when we talk about a cost equation, we said we call it C of Q, right? That's our dependent variable. So Q is our independent variable. So instead of mx plus b, we're going to have mq plus b. So just as a reminder, the m is the variable or marginal cost. And then the b is our fixed cost. Okay, so how much it costs, even if Q is 0. So if fixed costs are small, that means your B is small. That means that the place where we cross through the axis should be somewhere down here, right, on the smaller side. This would be a high fixed cost. This will be a low fixed cost. So we pick some point down near the bottom. But marginal cost is high. So that means that the slope of this line is large. And so if slope is large, it increases faster. So we want something that is steep, okay? So here, fixed costs are small, marginal cost is high. So we cross through low, but we have a steep line. It doesn't have to look exactly like mine. Yours might be slightly less steep or cross through somewhere around here. But those are the sort of the general conditions. We should cross somewhere in the bottom part of the graph, and then our slope should be steep in the positive direction because our cost will go up as we make more and more. Okay. Our second scenario that I want you to try to sketch is that there are no fixed cost. So fixed cost is 0 and marginal cost is small. Okay, so thinking about these words and in this context, how will that impact our line? So take about 30 seconds, try to sketch what that scenario might look like. Okay, so no fixed costs means that our B is 0, right? There are no fixed costs. So that means we're crossing through right at 0. And marginal cost, which we know is the slope, is small. So if our slope is small, that means that our line is not going to be very steep. So something like this, right? Yours might be slightly more steep, but it should not be as steep as that first one we were looking at. So we have something like this in this scenario. So the point of this exercise is to think about how these words like small and big, right? What those mean and how we translate those mathematically, okay? So continuing on with our cost examples here, suppose a company produces ceramic pineapples. The cost to purchase the pineapple molds and a kiln, which is like a really hot oven to like set the ceramics, is $20,000, which are incurred even if no pineapples are made. The cost of labor and raw materials, so the time to build it and like the clay, are variable costs, since these quantities depend on how many pineapples are made. The variable costs are $6 per pineapple. assuming that cost is linear, I want you to set up an equation for the cost function. So using the right variables, we're going to use C and Q. And then in part B, I want you to talk about what the marginal cost is and what it means in this context. Okay, so I want you to take about 1 to 2 minutes, right? Think about how we set that up, think about what that means, right? And then we'll go through it together. So jot down your ideas, and then we'll go through it in just about a minute or two. Okay, take about 30 more seconds. All right, so I know I want to use C for cost, C of Q, and now I need to think about the parts of the equation I need. So I know here that variable costs are $6 per pineapple. So that number 6 that shows up in my setup, that's going to be the slope, right? So that's going to be $6 times my variable, because the time or the number of pineapples I make impacts how many times I have to spend the $6, right? More pineapples, more clay, more labor, right? And we go from there. And then we need a plus B, right? So that's our fixed cost. So here, this is the cost, even if nothing else is made, right? That's our upfront investment. So 6Q plus 20,000. That's our cost function for this scenario. Part B says determine the marginal cost and explain what it means in this context. So again, for a linear function, the variable cost is the marginal cost. And so the marginal cost here is $6. And what it means in this context is that for every additional pineapple produced, cost goes up by $6. So something like this, right? So it's going to cost an extra $6 every time we make another pineapple. Okay, so that's sort of the overall punchline here. So that's cost. Okay, so what you need to know about cost is that, again, it's what it costs you to make a product, and that for now it's linear. And in this linear function, we're using the variable Q, that our fixed cost is our plus B, and it's our value when Q equals 0, and that our marginal cost is the same as variable cost when our function is linear. Okay, so that's the first sort of term that we need to work with. The next thing we need to talk about is called revenue. So revenue is the amount of money that we are going to take in from selling some number of our product. Okay, so if we were to, take our pineapples to the market and sell them for $100 each, right? Then our revenue would be 100 times the number that we sold. So it's the amount of money we get from selling what we're doing. Now we use R of Q to talk about revenue. So R for revenue. Q is still quantity. And so a general revenue equation, again, we're assuming is linear, is set up by doing price times quantity, okay? In this scenario, quantity Q is your variable, okay? Price will be given or price will be some sort of constant when we look at revenue functions. One thing we have to be really careful about is when we have a lot of information in the setup of a problem, distinguishing between cost and price, okay? Price is how much we sell an item for. That's it. Like, that's how you always want to sort of think about it. So let's look at a quick example. Suppose I've decided to open a store that sells gourmet cookies for $9.99 per tin. Set up a revenue function for my sales and determine my revenue if I sell 221 tins of cookies. So what I'd like you to do is take a minute or two, set up the revenue equation based on this information. And then once you have your revenue equation, plug in 221 for quantity to find the revenue that you bring in. Okay, so take 1 to 2 minutes, see if you can sketch that out, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so when we talk about revenue, we know that revenue equals price times quantity. So you'll either see this written as R of Q equals P times Q or R equals P times Q. They mean the same thing. And so here, if we want to apply what's happening in this problem, the price that we're selling them for is $9.99. So we have $9.99 times Q. So we bring in $9.99 for every tin that we sell. This is our sort of overarching revenue function. Now we want to know how much revenue do we bring in if we sell 221 tins of cookies. So we're going to do 221 as our quantity. So $9.99 times 221. We'll plug that into the calculator, and we are going to get $2,207.79. Okay, so when we talk about revenue and when we talk about cost, we're talking about money, right? So we're always talking about dollars here. And so if you end up with something with a lot of decimals, I just want to remind you that in our currency system, we round to 2 decimal places. So if you're not told otherwise, 2 decimal places is probably fine, right? Sometimes you'll be told to round to the nearest dollar, but here we'll do the whole thing out. Okay, so that's how we find the revenue for that amount of our cookie tins. Okay, so suppose that ceramic pineapples, remember we were finding the cost of those before, and now we're going to sell them, are sold for $20 each. Find a formula to represent the revenue function, then sketch the manufacturer's revenue function below. So I just want you to set up a revenue function and then quickly sketch what that line looks like based on what you know about linear functions. So just take a quick minute, see if you can write that out, and then see if you can think about how we would draw that line. Okay. So since we're selling these for $20 each, our revenue function is 20 times Q. So if we sell one, our revenue is $20. If we sell two, it's $40, so on and so forth. If we want to sketch this particular function, this is a linear term. So we would need 2 points that we know from this line, and then we can connect those points to figure out the line that we are going to be drawing. So we see here that if Q is 0, revenue is 0, right? So here we have the point 0, 0, and then I'm going to use the point 5 just because I have that easily on here, but you could plug in a 1 and sketch it, or 2 or whatever. So 5 times 20 is going to give us 100. So we have a line that connects these 2 points. So we're just going to do our best to connect these in a line, and that's just going to keep going up forever. Your line doesn't have to be perfect. We're just trying to get a general sense of what that's going to look like. Okay. So again, the key points of revenue is that it's how much money you bring in from selling your product. That revenue is price times quantity. That we have to be careful about what is price and what is cost. Price is how much we sell something for, and then we plug it into R equals P times Q. Okay, so that's our second term. So then the last sort of big picture term we need to talk about is profit, right? So profit is what you get when you take all your revenue, so the amount of money that you got from selling your item, and you subtract off your costs, right? The amount of money left is your profit. So when we talk about profit, we are talking about making and selling some amount of a product. And then the difference between revenue and cost is going to be your profit. So for profit, we're going to be using this lowercase pi. Now, revenue was R, cost was C. The reason we don't use P for profit is because P is already well known in mathematics for population, and we don't want to confuse it. And so here, pi is a better representation so that we know we're talking about something in business. I will mention that in Wiley or whatever, we're always using a lowercase pi. So make sure that if you're selecting pi from a menu, that you are finding the lowercase version for whatever it is you may be doing. So profit is going to be revenue minus cost. So again, the amount of money that you take in minus the amount of money you spend. I will note that profit can be negative. If you spend more money than you take in, then your profit's negative. That's not great overall for a business, but obviously when you first start a business, that's a pretty common scenario. And then what we do is we work towards a positive profit, right? You want to be making more money overall. So what we often look for in business is something called the break-even point. Okay, so the break-even point is where the profit is 0, which is the point where we're transitioning from having negative profit to positive profit. To go from negative to positive, you have to go through 0. So this break-even point is really important when you're doing business analysis. How long will it take us to get to the break-even point? How many do we have to sell to get to the break-even point? And so the break-even point happens when profit, which is revenue minus cost, equals 0. Okay, so we are assuming right now, because these functions are linear, that they are going up from left to right. And so we want to know when we break through and we get past that 0. Okay, so if revenue minus cost has to equal 0, that means we can also think about this as, let's see, I'll write it over here. Revenue has to be equal to cost, right? If we were to add that term over. So we are considering when these things are equal, when the amount of money you're bringing in is the same as the amount of money going out. So let's go ahead and take a look at this example. So find a formula for the profit function for the ceramic pineapples manufactured in the previous examples. So we want to graph the profit, mark the break-even point, and think about, how many we're going to need to sell in order to make a profit. So as a reminder, our cost function was 6Q plus 20,000. The 6 was our variable cost, 20,000 was our fixed cost. Oops, I'm missing the R. And our revenue was 20Q. We were selling them for $20 each. Okay, so again, what I want you to do is start by setting up the profit function. So we have to take the revenue function minus the cost function, and then you can simplify that if you're so inclined. Once we have the simplified profit function, we then want to graph it and try to determine from that where we break even. One thing that's going to be really important, when you are setting up a profit function and you subtract off a cost function like we have here, you need to subtract off the entire thing. So that means when you do minus, you want to put the whole cost function in parentheses. Okay, so I'm going to give you 2 minutes to work through this one, see what you can come up with, see how far along you get, and then we'll go through it together. Okay, so let's take a look at this, make sure we can get all the parts and figure out sort of what's going on and how we can do some analysis to figure out what we want to know. So again, we want to start by setting up our profit function. So we're going to do revenue minus cost. And so my revenue function here is 20Q, my revenue, minus my cost function. And so this is where I was saying we need to be really careful and subtract off the entire thing. So I'm going to use parentheses to make sure I don't lose the negative on any of the terms. So 6Q plus 20,000. So the minus has to go to both terms. So when we simplify this, we have a 20Q minus a 6Q. So that's 14Q. And then it's going to be minus 20,000 because the minus, again, goes to both terms. Oftentimes, if students get this type of problem wrong, it's because they didn't use parentheses and they ended up with a plus 20,000 or something like that. So just be careful about that. Now, we could certainly solve this algebraically for the break-even point by setting it equal to 0. However, we're asked to graph this and to look at the graph to sort of think about this whole thing. So you'll notice here that I have another linear equation. If you subtract 2 linear equations, you end up with another linear equation. So I have 14Q minus 20,000. So minus 20,000 is my plus B here for my profit. So that's where my function starts. And then my slope is 14Q. So I need to find another point on here. You can pick any point to work through it. So when you do, let's see, what did I get here? What we're trying to figure out, get something that looks roughly like this, okay? And what we want to know from this graph, from this line, is where we break even. And so the break even point for profit is where we cross through and where that profit equals 0, right? Because our profit is the dependent value So that profit's going to be 0 right when we cross through. That's what we're trying to figure out. We want to know that value. Now, that value looks like it falls between these two values. So I don't know exactly what it is, but I have a good sense of roughly where it should be because I can see that I'm counting by 5,000, right? So 5, 10, 15, 20. So somewhere between 10 and 15,000. Okay. How do I find it exactly? Well, this is where I'm going to use some algebra. So I take my linear equation, set it equal to 0, bring the 20,000 over, divide both sides by 14. And if you do 20,000 divided by 14, you're going to get 1428.57, roughly. Okay, so this quantity, right, where we break even is 1428.57. And so that means in order to make a profit, I would need to make one more, right? So I would make 1429 would make me a profit, right? Quantity is usually a whole number. So somewhere between right around 1428 is where we break even. So we would need to make 1429 to actually make a positive profit. Because remember that positive is above the x-axis. This is positive profit. This is negative profit. And we want to make money. Okay. So again, this point, this break-even point here, this is 1428.57, and the dependent value is 0. So that's our full break-even point. So again, when we talk about profit, we're really thinking about revenue and cost in relation to each other. Okay, so let's look at another example here. It's gonna hopefully help us think about transfer. Okay, so excuse me. So here we have a table that shows the cost of manufacturing various quantities of some item and the revenue that's obtained from their sale. So we have both cost and revenue in the same table. So for example, when you make and sell 20 of an item, your cost is $600 and your revenue is $600. Okay. So the first part of the question is what range of production levels appears to be profitable? So remember, profitable means that you're making a positive profit. So we need to think about how revenue and cost tell us about profit, and then figure out for which of these quantities we are making a positive profit. And then for part B, we want to calculate the positive profit or loss for each of the quantities shown. So this is the same table as this one. This just has an extra table line for you to fill in the profit. So I want you to think about what we know about profit, right? It's revenue minus cost, and think about how we might answer these two questions. So I'm going to give you 2 to 3 minutes to try to figure out the range of where profit is positive, and then also to find the profit at every single point. You can certainly do part B first to use that to answer part A, that's fine. Or you might be able to eyeball it. Either way is totally fine, okay? But take 2 to 3 minutes, see if you can work through these, and then we'll go through them together. Okay, take about 30 more seconds. All right. So what I'm hoping you sort of started to figure out is that in order for us to have a positive profit, we need our profit to be greater than 0, which means that revenue minus cost has to be greater than 0, which means that revenue has to be bigger than cost. If the amount of money we take in is more than the amount we spend, then we have a positive profit. So if we look at each step, we ask, is revenue bigger than cost? So here, no. Here, no. Here, they're the same. But here, 900 is bigger than 780. So here we're making a profit. Here, 1200 is bigger than 1000. Here, 1500 is bigger than 1320. So then here we have 1800, 1800. So that's the same. We'll talk about that in a minute. Here, 21, 25, that's a no. 24, 34. So what we see is that at 20 and 60 specifically, I'm going to mark this as break-even points, right? So something weird is happening in this particular table, right? This is not going to be linear, so we have to just use what we know. So we're breaking even right at 20 and 60, but between 20 and 60, we see that our revenue is greater than our cost, right? So what we can say is that for Q between 20 and 60, right, that's when we're going to be profitable, because that's where we're going to be positive. I'm not including it because right at 20 and right at 60, we're at 0. But certainly it's reasonable to assume that between these 2 points, we have this positive profit. Okay. For part B, we're considering the production level for each quantity. So that means for each one, we're doing revenue minus cost to determine the profit. So if it's negative, we have to include that negative sign. And again, it's okay for profit to be negative. So here we do 0 minus 120. So we have negative 120, right? 300 minus 400, negative 100. 600 minus 600 is 0. 900 minus 780 is positive 120. We don't need to write a plus if there's no negative there. It's assumed to be positive. 1200 minus 1000 is 200. 1500 minus 1320 is 180. 1800 minus 1800 is 0. 2100 minus 2500 gives me negative 400. And then 2400 minus 3400 is minus 1000. So that's the first part. Calculate the profit or loss for each quantity shown, and then estimate the most profitable production level. Well, since we have all the profits, we're going to be most profitable with the largest positive number, right? That's when we make the most money. So if we look at all these profits, that looks like it happens at Q equals 40, right? Then we make $200 of profit when we make and sell 40 of these items. So when we talk about production level, we are talking about the quantity. So we should be answering with the quantity that fulfills this approximation. Okay. So again, profit thinks about the relationship between revenue and cost. And so profit, revenue, and cost are the 3 things we're going to be thinking about and doing applications of throughout the course. Okay, so let's look at another example of how this comes up, just to sort of summarize what we've been learning. So the marginal cost, marginal revenue, and marginal profit. So just like we are thinking about rate of change, we know that for linear functions, marginal cost is the same thing as variable cost. Marginal revenue, okay, is going to be the slope of the revenue function, which we know is the price, right? So we had price times quantity. Marginal profit is the slope of the profit function. So we would need to simplify our profit function by doing revenue minus cost and then finding the slope. Once we know the slope, we know the marginal profit for that item. We use the term marginal because we're looking at how things change at the margins, which means what happens if we make, sell, or make and sell one more unit, right? It's called on the margins because we're asking what happens if we do one more? What about one more? And we're trying to determine, is that good for the business? Is that bad for the business? Should we make one more, right? So that's what this word marginal means. So for right now, we know this has to do with slope. Later on, once we move away from linear functions, we'll talk about how that impacts what we're doing with our economics examples, okay? So for example 7, we're just sort of tying in all these things we've been talking about. So I'm gonna have you try this. The idea is that we have some item and the cost is given by 8,100 plus 4.45Q. The revenue is given by 5.65Q. And then we have a whole list of questions related to what we've been talking about. So what is the fixed cost? What is the marginal cost? What is the price? And what's the name? Like, what do we call that? What is the profit when Q equals 1,000? So you'll need to set up a profit function. What level of production does this company need to reach to make a positive profit? So now we're talking about the break-even point. And then when this company produces and sells one additional item, what is the marginal profit? So we would need to have the profit function to figure out the marginal profit, okay? So take about 2-3 minutes. You can jump around, you don't have to answer these in order. See what you remember, see what you can figure out, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so I just want to mention quickly that as we do practice problems in class, it's totally fine if you don't finish them. We have a lot to go through, so we won't always have enough time for you to finish all of the problems. But as long as you're starting them and thinking about how to set things up and getting some of it done, that's what really matters. So don't feel like if you're not getting it done in the time I give you to work on it, that there's something wrong. Because typically we need a lot of time to really think about it. We just don't have a ton of time in class to get through all the material. Okay. So part A, what is the fixed cost of the product? So for fixed cost, we want to go to the cost equation. And we remember that our fixed cost is our plus B. It's the amount of cost when our quantity equals 0. So if this term is zeroed out, what's left is this plus B, which is $8,100. Okay, so our fixed cost, that's how much it's going to cost us, even if we didn't make any of our product yet. Part B, what is the marginal cost per item? So remember, marginal for linear functions is the slope, and it tells us how much additional cost per item. So it looks like here, it's $4.45. Okay. Part C, what is the price this item is sold for? What is this called? So the price, remember, comes from our revenue over here. And so our price in the function is price times quantity. So here it's going to be $5.65 is the price that we are selling this for. Another name for this is marginal revenue. Okay, because again, marginal is the slope of a linear function. Part D says, what is the profit when Q equals 1,000? Well, in order to start talking about profit, we're going to need to figure out what the profit function is. So remember, our profit function is going to be revenue minus cost. So my revenue is 565Q minus cost. And again, I'm going to use parentheses. So 8,100 plus 4.45Q. I want to simplify this by combining like terms. So I have 5.65Q and then a minus 4.45Q. So that's going to be 1.20 or 1.2, means the same thing. 1.20Q minus 8,100. So again, make sure the minus goes to both terms on that cost function. And so if I want to know the profit when Q equals 1,000, I need to plug a 1,000 in. So Q of 1,000 equals 1.2 times 1,000 minus 8,100. When I crunch that number, I get minus 6,900. And I just did that quickly on my calculator. So I see that profit's negative when I make and sell 1,000 units. Okay, so far I'm losing money. So the next question is, what level of production does this company need to reach to make a positive profit, right? So what we need to do is we need to think about what's called the break-even point. So to find the break-even point, we want to take our function, 1.2Q, let's do it this way, minus 8,100 equals 0, right? Then we bring the 8,100 over. So 1.2Q equals 8,100. We divide both sides by 1.2. And we get, let's see, 6,750. So we need to make and sell 6,750 units to break even, which means that in order to make a profit that's positive, we would need to make and sell 6,751 items. So we need to do one more than the break-even point to make a positive profit. Okay, so this is the break-even. And then we'll do this in another color. So Q equals 6,751 to be profitable. Okay, so those are two different things we can ask. The break-even point is when you solve, but to be profitable, you need to go to the nearest next whole number, right? So we add 1. So part F, when this company produces and sells one additional item, what is the marginal profit? So we want to go back to our simplified profit equation, which is here. To get the marginal profit, we've simplified revenue minus cost, and we're looking for the slope of the line. So here, the marginal profit is $1.20 per item. So that means that for every additional item that we make and sell, our profit goes up by $1.20. So that's how much we make, each extra time. Okay, so these are sort of the general types of things we can ask about. These are the things we're going to be building upon. And these sort of are all related to our business. There's one more application that we need to talk about, which is the depreciation function. So in business, oftentimes when you buy something, it goes down in value, right? A car is sort of the most common example that we usually talk about, although cars right now are, in high demand. But when you have an item that loses value over time, we say it depreciates. So the depreciation function is a formula that has the value V in dollars of some item as a function of the number of years T since the item was purchased. And so when we talk about depreciation, we assume that the value depreciates linearly. So we can use this to figure out, how long the item has value, when it will reach a value of 0, things like that. But the idea is that we're still thinking about the value and sort of overall marketability of a product. And so all we need to do here is think about how to set up that linear function to represent the fact that we are losing value. So just to sort of give you an example of what this might look like, suppose that the ceramic pineapple manufacturer has a machine that costs $16,000 and is sold 10 years later for $4,000. We say the value of this machine depreciates from $16,000 today to a resale value of $4,000 in 10 years. We want to find the linear function that represents the depreciation of this machine. So what we need to think about is what is our independent variable, what is our dependent variable, and what sort of information do we have? So here we're varying time, okay? So we know something about when time equals 0, and we know something about when time equals 10. And what we know is the value at these time points. So at time equals 0, our value is 16,000, right? And at time equals 10, the value is 4,000. So what we want to do is set up an equation that will tell us the value at any time. We know it's linear, and we have 2 data points, so we can use that to find the slope and R plus B, okay? So to find the slope, we're going to do the change in Y over the change in X. So we have 16,000 minus 4,000 divided by 0 minus 10. Okay, so on the top, we have 12,000 divided by negative 10. So negative 1,200 is our slope. So we have negative 1,200, and our variable here is time T, plus B. So B is the value when time is 0. For us, we actually already know that value because that was one of our points. So here we would plug in 16,000. If we didn't have this particular point, we would just plug in both the dependent and independent value and then solve for B. We'll get the same thing. So now what this says is we can figure out the value of this machine at any given time, right? So initially when time was 0, the value was 16,000. If we wanted to know the value after 1 year, we'd plug in time equals 1. After 2 years, time equals 2, so on and so forth. And we could figure out things like when is the value 0, what is the value after 5 years, all those sorts of things. But when we set up the depreciation model, what we're doing is we're using the information about the value at 2 points to get the linear model that tells us the value at any point. Okay, so that will come up, I think, on the homework. So I want to make sure you saw an example of that. So we're going to transition over to talk about exponential functions in a second, but just as sort of a quick recap, a lot of the stuff that we talked about just previously has to do with business and economics and models, and we'll be sort of touching back to this in every single chapter. So we really just want to make sure we have a good concept of cost, revenue, profit, and these sort of things that we've done with them. Okay. Okay. So exponential functions, I'm sure you've seen these in your life, whether or not you remember how they work, it's another question, but exponential functions are functions of the form y equals k times a to either the x or the t, whatever your variable may be. And so the way we recognize exponential functions is that the variable is in the power. Okay, so that is different than, say, x squared. X squared has the variable in the base, but when the variable is up in the power, that's how we know it's an exponential function. Okay, and so with exponential functions, the variables in the power, which means the base, like this a, is a constant, it's a number. And if there's a k in front, then that's also a constant. The thing that varies is up here in the power. So for each of the following exponential functions, compute the value for t equals 3. So what I want you to do is I just want you to take a minute, try 1 or 2 of these with your calculator, and just make sure that you're comfortable plugging in values into exponential functions. Okay, so I'm going to give you 1.5 minutes, try 1 or 2 of them. As long as you can get 1 or 2, then we'll be pretty good in making sure that we know how to plug them in. I would recommend at least trying D, which has the E in it, so you know where the E is on your calculator. Okay, so just take a quick minute, try 1 or 2 of those. Okay, take about 30 more seconds. And if you're having trouble plugging things in and getting the right number, you can definitely stop by Drop and Help, and we can help you with the syntax just to make sure. And I'll show you on my calculator in a minute, or I'll put it up now, what it sort of looks like in case you have a TI. TIs all sort of work the same. Okay, so you can see here on my calculator, I did A and D, the first one and the last one. So to do the 2, right, I press the 2, and then the multiplication button's over here. I'm just going to repeat the last one just so you can see where it is. So my E button is hidden behind this ln, so I had to do second, and then this, which puts the E in, and then the power is blinking, and I entered the 3 because t equals 3 here, and hit enter. Right? So we just want to get comfortable making sure we can enter things up into the power. You're probably fine with this, but just in case it's been a while, I just wanted you to practice it once. Again, if you're not able to figure out the syntax, stop by Drop and Help. We'll help you. Okay, so that's plugging things into exponential functions. So the reason we talk about exponential functions is because when we think about growth and decay in the natural world, it's almost always modeled exponentially. So when you think about like carbon decay and carbon dating, when we think about chemistry and how quickly catalysts break things down, most of these are exponential functions. So it turns out we end up working with them a lot if you're in the life sciences. So we want to be comfortable sort of setting them up and evaluating them and knowing what the different parts of the exponential function means. So a couple things of note for exponential functions. Almost always the variable is t. It doesn't have to be, and so you need to be a little careful and wily to make sure you use the right variable. You can see up here I used x. But the reason why it's commonly t is because we're usually measuring something over time. And so t ends up being a natural variable for that. When we think about the general expression for growth and decay, we are commonly going to see it written like this, which is slightly different than the y equals. Okay. And well, I'll come back to that in a second. So as I mentioned with the economics, we don't tend to use P for profit because we use P for population. Okay. So in this exponential scenario, this is probably modeling some sort of population. So P is a common dependent variable you will see when we're talking about something that's using exponential functions. Now here, this P naught, okay, represents the initial amount. Okay, so think of that 0 as like the starting point. So if we're talking about like a population of penguins, right? And this number says 700. That means that initially there were 700 penguins, right? So whatever is here is whatever amount we're starting with for whatever we're measuring, okay? So both P naught and A are constants. So the variable is the variable in the power, which is usually T. And so when we talk about what these pieces mean, the base A is where we do a lot of our work, okay? So T is where we're plugging in numbers like here. P naught is the initial amount, but this A, which is the base, has a lot of really interesting information for us. And so one of the ways that we can somehow rewrite this to think about A looks like this. Okay, so A is actually 1 plus R. So that's happening sort of in the background. So what's R? R is our rate of change. So if we are growing, then our R is positive. So if we're growing by 10%, then R is 0.1, right? If we are decaying, then our R is negative, right? And so this 1 says, okay, how much was the original population and how much was the change? That's going to be our multiplier, okay? So if A is greater than 1, so if the number that's in the base is bigger than 1, what that means is that we are growing. And we're growing because the rate was positive, okay? If A is between 0 and 1, so less than 1, but still positive, that's when we have decay. And that means that our R was negative, okay? Your A will always be positive, so you don't need to worry about a negative in that situation. So when we started, we were talking about linear functions. Linear functions have what's called a constant rate of change. So every time you move 1 unit in the x direction, you move the same amount in the y direction for a linear function, right? Exponential functions have a percent rate of change. So every time you move 1 unit in the independent direction, you change by some percent in the dependent direction. So that's why it doesn't change quite the same. And so we want to be able to look at functions and think about their rates of change, think about how they, work and distinguish between linear functions and exponential functions. So let's look at an example. Let's see. Yeah, I guess we'll look at an example too. Okay, we won't get through all the examples. So if it's been a while since you've done exponential functions, the other examples you can find in the videos to look over, or you can read the textbook section. It's only a page and a half. But let's look at example 2. This really sort of brings in all the things we're talking about with exponential functions. So suppose that the 4 functions below, so 1, 2, 3, and 4, represent the population in thousands of a different town and how its population changes over time t in years since 2010. So we have 4 different towns here and how they're changing since 2010. We want to know, A, which town has the largest percent growth rate? So that's that R that I was just talking about. So that has to do with the base number. Okay. B, which town has the largest initial population? So that's the P naught. Which one is the biggest? Which town has the largest population in 2015? So we have to compute the size at time equals 5. And then D, which towns are growing and which towns are decreasing? So that's looking at this base A and figuring out, is it bigger than 1 or less than 1? Okay, so I want you to take about 3 minutes, 2-3 minutes, we need enough time to go over it before we leave, to try to answer these 4 questions, and then we'll go through it together. So jot down what you think, and then we'll go through it. All right, take about 15 more seconds to finish up your thoughts. All right, so what we want to do here for part A, which town has the largest percent growth rate? So the growth rate is your R, and as a reminder, the R is from that base A. So for this first one here, if A is 1 plus R, then my R has to be 0.37. That's what got added to 1 to get 1.37. So that's my rate here. For the second one, I noticed that my base is less than 1, right? So that means that my R had to be negative. My base is 0.68 equals 1 plus R. You subtract the 1 over, and you get that the rate is negative 0.32. Over here, similarly, for population 3, I see that my A is less than 1. So I have to subtract 1 from here, and I get negative 0.65. And then for the number 4, I have 1.28. So my R has to be positive 0.28. Okay, so once I have all my R's, I want to compare to see which one is the largest. And so when we talk about largest, I want you to think about R as if we were on a number line. Okay, where 0 is here, and which one is going to be the highest on that number line. So looking through those, that's going to be the 0.37. So that's going to be number 1. For part B, which town has the largest initial population? So remember, that's our P naught. So that's the number in front of the A. So we're just comparing 250, 1200, 125, and 500. 1200 is the largest. So population 2 has the largest initial population. For part C, which town has the largest population in 2015? So that means that we would need to plug in a 5, right, into each of these models to see the size of the population after 5 years. So for the first one, we're going to get 1207 when we plug in a 5. For the second one, we're going to get 174. For the third one, we're going to get 0.656. And for the last one, we're going to get 1718. Okay, so comparing all those values, we see that town number 4 has the largest population after 5 years. Some of them are growing, some of them are decaying. So really the only way to compare is to find the population for each of those. And then for part 4, which are growing and which are decaying. So again, we're going to go back to our R values. We're going to be growing when your R is positive or when your A is greater than 1. So that happens in town 1 and town 4 are growing. And we're decaying when your R is negative or your A is less than 1. So 2 and 3 are when we are decreasing. Okay, so we're able to look at that analysis, figure out what's happening there, and then, work within the bounds of our exponential functions. I'm going to give you the solution to example number 4, and I would like you to try it at home. Okay, so I just want you to jot down this final answer and make sure that you can get the same thing. Okay, so this is 80 times 1.1447 to the T. Okay, so I want you to try this problem at home. Make sure you can come up with this as the model. And if not, stop by Drop In Help. That's sort of the last thing, is like computing a model from data. Okay, all right, have a great rest of your week. I'll see you guys on Thursday when we'll be talking about old functions, new functions from old.